Okay, so today we'd like to actually finally formally, even though you've already thought a little bit about the fact that the concepts we've been thinking about over the last months here are connected to extreme values of functions, we need to like come out and say this. So this is the day to do it. Okay, we're gonna finally have a little bit of a heart-to-heart about like when do we expect maximums and minimums on curves. So today's finally the day. We should give kind of, before we begin, maybe a real-world disclaimer. At this point in your life, it's pretty clear to us too that we could like use our calculator. In fact, you've been finding maximums and minimums all along in life. So why is calculus necessary for finding maximums and minimums? It might be necessary for other things. So you can read my little paragraph here if you like. Important and beautiful. And it's on the test. I should say another reason too that we'll discover later too. We should be the kind of people in this world who can program calculators, who can like build the machines that do the work for us, right? So we'll learn, for example, like here's an easier problem that you've been solving all along. How do you find the zeros of a function? Yeah, and again, like if it's not nicely factorable, if you have like a really messy function, how do you even find the zero of that function? How do you solve equations in general in life? And a lot of times your answer is like, I don't know, I look on the calculator. But how did the calculator get programmed to do that? Well, we're going to learn an algorithm this year called Newton's method that will show you how what your calculator does to get those roots. So for example, right? So lots of good reasons to do it. You'd like to understand what's under the hood, you know? And also it is beautiful and it's fun. All right, so the first kind of extreme value we should mention is maybe an absolute extreme value. And this is terminology I think that you've heard even back as far as Algebra 2 or whatever. You've thought about what maximums and minimums mean. So we're talking about either an absolute or a global extreme value, or extrema, sometimes we call them. If we want to sound fancy, we use the Latin. So those are words I think you've used before. I think extrema is the word AP likes best, the Latin. So that's what it means when they say find the extrema. So I think they use the Latin extrema.
Wait, so like,
they will say absolute, I think. I think they don't usually say global, which is weird because they talk about local, you know. So maybe you haven't ever stopped to like do some soul searching on this question, but when do we expect extreme values to occur? Like this mean value theorem, we had some conditions. Could we find some conditions under which we can guarantee that there will be a maximum or a minimum? Can you think of some, especially if you haven't taken calculus before? I'd love to hear from you. You have a suggestion, John? Okay. Yeah, I guess I would even think, I'm thinking even more simply, like, how about this graph right here? Does this have a maximum and a minimum? Like, when can we guarantee that both a maximum and a minimum occur for a certain function on a certain domain? Yeah. It's definitely going to have the derivative's going to come in for sure later.
Maximum occurs when there's no f of x higher within a given like plus or minus tolerance, and you can put that tolerance for anything you want. Like for any given tolerance, there's no higher value within x plus or minus that tolerance.
Yeah, I'm trying to give a. I don't know what you mean.
So like if I give you an x and y value,
Okay.
and I give you a tolerance for x and y, so sorry, just for tolerance for x. Like if I just give you a number, any number,
Okay.
and an x value and a y value, And for every f of x between x minus that number and x plus that number, there's no y greater than the y in f of x.
I think I see where you're going with this a little bit, but I think that like a graph like this might contradict what you're saying. Like this doesn't have a maximum, even though I think it meets your criteria, doesn't it? Like it is bounded, right, above, but it doesn't have a maximum. Albert, chime in.
I have an idea.
Okay.
It sort of branches off what Jonathan said. When the derivative of a certain equation crosses the x-axis,
Okay.
it creates a mixture.
Okay. All right. That's yeah. And does that still help me in this situation with this graph from 45, for instance, though?
Maybe, no.
I mean, I'd like to think. Well, let's just ask for this graph. Does this have a minimum value? This function on the domain 0 to 1. It's defined only for value 0 to 1. So does this function defined for on the closed interval 0 to 1? Does it have a smallest value? It certainly does. It's 0, and we can all say it's certainly, and we can give actually two different values of x that demonstrate that value. So great. Does it have a maximum value? It actually doesn't have a maximum value. So here's an example where we don't have a maximum. We definitely do have a minimum. I think you're maybe thinking too hard about it. We will talk about the derivative soon here. Let's see if we can tease this out here. With more examples like this one from 45. Keep in mind that extreme values could be interior points, which is what you're kind of getting hung up on, thinking about the derivative. We'll say that for sure. But it could also be an endpoint too, like we just talked about. So let's look at this first function. Here's one. We'll see if we can develop some criteria as we go. Again, my question on each picture I'm going to show you a couple pictures, is does it have an absolute max? Does it have an absolute min? I want to answer both of those questions. This one, does it have one or the other or both? Which one is that? It has only an absolute minimum, no absolute maximum. Okay, how about a new one here? This time I'm only looking at this graph, but only on the interval, the closed interval, 0 to 2. Now answer the question. Yes, and yes, has both. Good. Wonderful. All right, let's see another picture. How about the half open interval, 0 to 2? How about that? Yeah, it has no absolute minimum this time, right? But it does have an absolute max. What about the open interval? Of course, the answer is no and no. Good. Now notice here, I haven't even brought in the interior points yet, right? I haven't brought in interior. It could be that we have some other interesting function that goes up and down on the inside too. But just with the endpoints in clear view, what do you think needs to be true? Yeah, there needs to be like a point, like on both ends, right? I mean, I don't know how else to say that. Well, we could say it needs to be, what was the criteria here for the mean value theorem? Maybe we can steal it. Yeah. Yeah, it needs to be continuous on whatever the domain is. Yeah, on a certain closed interval, right? So here's this is the only thing we need, is that we have a function that's defined and is continuous on a closed interval. Then that we're certain that we will achieve an absolute max and an absolute minimum. That's all. That's all. Now, of course, like I said, we thinking about interior points is part of the discussion too, for sure. So let's continue that discussion. So here we have, for example, on that particular function defined on a closed interval, we have maximum and minimum that we've achieved, and they happen to both be interior points. Here we have them both being exterior points, or endpoints, boundary points, whatever you want to call them. That's very similar to the examples we were just looking at. Or it could be here where we have the absolute maximum is an interior point and the absolute minimum is an endpoint, right? So all those things could happen, just to be clear. So we probably should have put a box around this statement at the top. This is actually the statement of the extreme value theorem up here, right? There it is. Very simple hypothesis. Josh.
For a function y equals x, does that mean at every point we have a maximum in, or at no point is it a maximum?
So you need to define it on a closed interval. If you define y equals x and your domain is negative to positive infinity, that's an open interval.
What about, I mean, y equals 1, so I meant to say, so I mean y equals 1 from say,
Yeah.
negative 2.
Oh, yeah, yeah. So that's, so what is the maximum value of that function? Did you say y equals 1?
Yeah, I
Okay.
mean 1.
Yeah, 1. And what's the minimum value?
1.
Great. Let's, next example. Yeah, we didn't talk, like, one of the examples we did earlier, or the one we're looking at on the board here, right? We said the minimum value, there are 2 times where it occurs. Is that okay? Sure. Could it be okay if there are like an infinite number of times that that minimum value is achieved? Sure. Yeah. Yeah. The question is about f of x. Does f of x have a minimum? So the answer is yeah, it will. All right, we can come back and talk about what a local maximum is and a local minimum. That's, again, some pre-calculus knowledge there, too. Maybe we spend some time saying what we actually mean by this definition right here. I think all of us intuitively understand what a local maximum or a local minimum is. But again, we mean, what does this mean? Can someone kind of explain what the text, like, give me some precise description of what that means. I think we all have a feel. I have a picture here, by the way, too. Like, this is a local max, right? Like, we all kind of know that. It's not the biggest. It's like, but like, what is this? What does that language mean? Steven, you want to help us out?
Yeah, okay, so like a local maximum, so you have like a, for example, of that graph right there, like at that first local maximum right there, yes, you can go like an inch to the left and the right, and that's the one giving you, and then after that point right there is the highest point on that interval, which means it's a local maximum.
No, but what if you take a bigger interval, like from here to here or something? Then it's not the biggest value, right? No, I'm putting you, I mean, you said it right. I'm just like intentionally being mean here, just like playing devil's advocate.
If you put it before the hump, there
Okay.
would be no open interval before. Sorry, on the other side of the hump.
Oh, yeah.
There's no open interval where that local maximum, the endpoint is open.
Yeah, the best way to think about this is to claim that this is a local maximum, and then talk to me about why the definition doesn't qualify, maybe, right? Or how about the one on the board? Why isn't this a local maximum? Right, Albert? Or you can answer any of those questions.
Okay, well, okay, I guess I can first answer the question. I think it's like forever approaching that point, but it never
Okay.
actually reaches that point, so it's no like absolute maximum.
Okay.
It's always like.
Does it contradict this definition of a local maximum? Because it should. Otherwise, you know what I'm saying? Like, or
Right.
or like take Judah's example. Like, say we say this point is a local maximum.
Yeah.
It isn't. We all kind of know that in our hearts. But why does it violate the definition? Couldn't you find an open interval that I don't know? Yeah.
Yeah.
Oh, you want to say something else?
Question. Like, what if we have an equation where as f of x approaches 0, I mean, as f of x goes to plus or minus infinity, f of x goes to sorry, you know, like
Yeah,
on
yeah.
both sides it goes to 0,
Okay.
right? But in the middle it goes
Sure.
with the curve. Doesn't
Yeah,
that
yeah.
violate this definition? Because
Right here about local maxes and mins,
Yeah. I mean,
or
isn't
about
that
the
like-
extreme value theorem.
I'm worried about, I mean, like, because it says within some open interval.
Yeah.
And like in the example that I gave, it both goes to 0, but it's still like the largest value. Does that still qualify as the local extreme value?
Those are local extreme values.
Okay, then I'll.
Let's hear from someone else here. Josh.
Even
chime in.
the open interval, that would mean it's non-inclusive. So with that point you keep pointing at right there, there's no way to make a non-inclusive interval in which that's still the local maximum.
Yeah, can you find an open interval containing this point where it's the biggest value? Not an open interval. Yeah, the key word is an open interval containing that point. There is no open interval that contains that point where it's got the biggest y value. Yeah, did you want to add to that? Either of you? No. Okay. Yeah, and also the key word here is some. Not that qualifier is an important word too, right? It's not that true that on every open interval that someone brings forward it needs to be the maximum. You get to pick it. If you can find, I'll challenge you, if you can find even one interval, open interval that contains the point where it's the biggest, then it is a local maximum. Yeah, Steve.
I want to answer the question that you asked me.
Go ahead.
I don't believe that.
I don't remember what that was, but go ahead.
So like I said that it was like given an interval from A to B.
Okay.
And it was, and then you said like so.
Yeah, yeah,
if
yeah.
I say that interval, then how come it's not local max? Because the derivative changes signs at that point from positive to negative. Like no, not that. Like,
Well, no, I know. I think the question. I was kind of pushing you on the word sum a little bit. I was thinking like, what about this open interval from like here, all the way to like here? And the answer is, as long as you can. You said you could just tell me like, no, I don't want to think about that interval. I just want to think about this interval. And on this interval, it is the maximum, so go away. Like you could just say that, right? Does that make sense? Like you don't. It's not true that for every open interval it has to be the maximum. You just have to find one. So then you're good. Yeah.
Is this just a restatement of there exists an open interval where that point is?
Absolutely. Yeah. Yeah. So absolute minimum, also a local minimum by the definition above. Local maximum, local minimum, absolute maximum. All right. So I think and these are also called relative extremes. So, by the way, why is this a local minimum? By this definition of local minimum. Yeah, Jonathan?
How can you make local minimum? How can you make a local some open with that?
Yeah, right. And the answer is, I mean, if you put an open interval around this, like this function is only defined here. It doesn't. It's not like it keeps going. So it is actually the lowest value. Like to the left, it's not defined. So we're okay.
So could we use a value to the left if it was a smart interval?
Yeah. I mean, we're talking about an interval of x values. So yeah. All right, now we're finally ready to answer the question that like every single person has been like answering instead of the other questions. We haven't even talked about like really calculus things yet today, have we? We've only been talking about all these things. We haven't mentioned the word derivative yet. So I think we're finally ready to actually think about when do we expect local extremes. So this is what I think some of you guys have been saying. Like we like thinking about the derivative. It seems already, even in our first 2 months of this course, that it seems like the derivative is intimately connected to the idea of a local maximum or local minimum. But this language has to be couched very, very carefully here. If a function f has a local max or a local min, first of all, why is that condition necessary? Then it follows that f prime of c equals 0. Why is that condition? First of all, it has to, I'm just saying that is to say, if you have the derivative 0, does that mean you have a local max or min? Give a counterexample.
No, y equals 10.
Yeah, y equals 1. Okay, I was thinking of something curvy actually. Can you think of something curvy that has a derivative of 0 somewhere that doesn't have a local max or min? Yeah. Yeah, y equals x cubed is kind of my go-to example, right? For a function that does have derivative 0 at 0, but does not have a max or min there. There's another piece that's really important though, and that's this. So if a function f has a local max or a local min, and f prime exists, then f prime of c better be 0. Why is that necessary? This is actually critical. It's not just like kind of, ooh, mathematicians mumbo jumbo in there. Why is that critical? Again, maybe come up with a counterexample where. Yeah, a corner or a cusp or something, or in general, somewhere that we don't. Yeah, the absolute value function is a good example, right? Does that have a minimum? Absolutely. In 2 senses, yeah. But yet the derivative is defined there, so we want to be careful with this. And all the things that are said in this sentence are all necessary. Yeah. So let's go back to this picture here. So yeah, in fact, here we go. If the derivative is defined here, which it looks like it's smooth, looks like it is, and that's a maximum, then it better have a derivative of 0 there, and likewise here. And again, like I said, the converse is not necessarily true, and you guys already gave an example. But what about this point? This is the case that Stephen was talking about. In fact, we have it on the picture we've just been looking at. Is the derivative of 0 there? No. Does that contradict what we just said here? No, because we saved ourselves by saying that. F prime doesn't exist there. But of course, we're interested in places where the derivative is 0. That's a great first place to look. So we're interested in that. But we just now realize maybe too that we should also look for where the derivative doesn't exist. So those are our those are our key important points. We're going to call them critical points and put it in bold and italics. Okay, that's going to be our short list. We're going to check critical points. If we're looking for extreme values of the function, we're going to check places where the derivative is 0, places where the derivative is undefined. Those might not all yield maxes and mins, but we're going to check them, and endpoints, right? So here's places where the derivative is 0. Here's a place where it's undefined. I should have on this picture, just to be really complete, we should have also had a place where the derivative was 0, but there wasn't a max or something like that. Likewise, if the derivative is undefined, that doesn't necessarily mean it's a max or min either. When you think of a case where that happens. 1 over x. Yeah, okay, it's not even continuous there. That's right. Yeah. I was thinking of like the cube root of x as a place at 0 where it's undefined. But that's not a maximum either. Sorry, it's went too fast. So critical point is an important word, I think, for us. This idea of a critical point. I mean, important enough that like AP will actually ask you, and we will ask you, like, give the critical points. Name them. That is all the candidates that could be maxes or mins. So you need to like know what we mean by the word critical point. So all places where the derivative is 0 and the derivative is undefined. Okay. And I think we already said that. So, and I already even mentioned these two examples. So there they are. The cubic function and the cube root function are good examples of contradictions to the converse of that, right? Clearly, just because something's a critical point doesn't make it a max or a min. So there's your word of caution. Just look at those pictures, remember those, and be like, oh yeah, I know that can happen. Anything else you guys want to say? You didn't know we could go into such depth on the extreme values here. All right, well, we've got to do an example, of course. So this is actually one I think that's directly from the book, actually. X to the 2/3 on the interval negative, the closed interval, -2 to 3. Why can we, before we begin, this is a well-formed question. Will there be an absolute maximum, an absolute minimum on this curve?
Yes.
Definitely. Why?
Because it's closed.
It's closed and it's continuous on the closed interval -2 to 3, isn't it? Okay. So that's good. That's all we need. We just need it to be continuous on the closed interval. I'm going to take the derivative, like, just for fun, but why is that interesting? What does that tell me as soon as I see it? You haven't maybe thought about what the graph of this looks like recently. I don't know. There's a point where, yeah, looking at the form of the derivative, even if we haven't thought about the picture yet, is the derivative, I guess the big question we keep asking ourselves is the derivative ever 0 or undefined? And the answer is it's not ever 0, but it is undefined when x is 0. So that's our critical point. That's the only critical point for this simple first example. So 0, 0 is critical point. Again, we're looking for maximums and minimums on this function that only lives on this domain. So check the endpoints as well. So check the critical point value, check the endpoint values. There's one and there's the other if you plug them into the original function. These are the only things that even could be maxes and mins on this closed interval, right? we have a very short list of 3 things. So I think we're ready to make our conclusion. What's the maximum and minimum value of this function on this interval? Yeah, q root of 9 is the biggest it'll ever be, and 0 is the smallest it'll ever be, and we can even say where those things occur. Right? I'll show you the picture of this in a second. I mean, you probably, maybe you already have a picture of what it looks like in your mind. But. I mean, obviously, when you're actually doing this kind of a problem, you won't write as much as maybe I did, but I just wanted to make sure you're clear on the reasoning. I can come back to this in a second. I just thought I'd show you the picture here, too. There's the picture of the function we've been working with just now, right? Does that make things a little clearer? Yeah, in fact, yes, there is a minimum value. The minimum value is 0 and it occurs when x is 0. The maximum value is, it's not 2, looks like it's 2, but it's the cube root of 9 is what we said it was, or 3 to the 2/3. 3 halves. No, 2/3. Yeah. So anyway, and of course, we don't have an absolute max over there at all, right? Did anyone need that for another second? I didn't. Huh? This makes me think too that I think you're used to having someone hand you a function in life and not also hand you the domain, but maybe you're starting to see that actually in higher level math, it doesn't ever make sense for someone to hand you a function without also first telling you what the domain is. I mean, think about that in real life too. What does this function accept that you've just handed me? You need to tell me what I'm allowed to put into it that makes sense. There might be all sorts of real world constraints if it's a model of some kind. Maybe it only takes integer values. Maybe it only takes positive values for certain because of the context of the problem. So, in fact, it's very common in higher level mathematical literature and in college courses, if you take math, to write, let f be a function from, well, here in this case, -2, 3 to the real numbers. That just means this is the domain, and that's where we're sending numbers. Obviously, that's not the range though. And people would just always give defined by this function rule. Right? They always give the domain and the function. So more and more we are doing that too, I guess, too. All right, so here's our easy 2-step process just to summarize. Okay. Obviously, this is just the tip of the iceberg as far as finding extreme values go. We need to kind of lay this theoretical framework first, though, I think, to really understand when do we expect to have extreme values, for sure. But then obviously, finding the places where the derivative is 0 or undefined could be non-trivial, right? That was easy to find where the derivative was 0. Actually, the most annoying part of the problem was plugging the endpoints and the n0 in and actually trying to figure out which was the max or min. The calculus was not very interesting. It wasn't at the forefront today, but it will be as we keep moving forward. We're going to have complicated functions that we'll have to find places where it might be 0 undefined, and that suddenly becomes a problem sometimes, right? We have a lot of work to do there, maybe. Might happen in multiple places, finding all the local extremes or something. think that's all I have, yeah. And we'll say more about that as we talk about the first and second derivative tests in the coming days. Any other thoughts or questions